Okay, we are live now.
Great. Sure wish Kimberly would show up to these. Oh, look at that. Hi, everyone. I'm on Linux now, which I love, but things play a little different with Linux than with Windows. And I can't expand to see, I can't expand the camera windows of each individual, but it at least shows me a little strip. So I guess we're okay. All right. I want to explain something. This is going to be the last lecture on regression. And it's going to be very similar to the last few lectures I've done, will be very similar in format to the last lectures that Guy's going to do on classification. And you'll see some patterns. The biggest difference, of course, is in the algorithms you choose and in the metrics you choose. And the reason I've been more regressor-centric in my career is because of my background. And the reason Guy has been more classification-centric is because of his background. But they're both important and valuable. And one of the fringe benefits that Guy shared with me about our association is when he was working on a classification problem recently, he found it more expedient to give more insight to a client to kind of make it a hybrid where it was a combination of regression and classification. And we were both excited that that had come out of our relationship, but I've been excited to get a more intuitive feel for classification metrics. And if you followed my LinkedIn posts, you can see my some of the more recent ones, my joy in really getting down and dirty with pseudo math on certain classification things. But for model selection in regression, prior to this point, what have we been doing? We've visualized data initially and frequently as we go through pipeline development. And we've cleaned data, and we've done this acyclically. We may get later down in the process of getting the data ready for modeling, and we find more dirty data. You never know when it's going to reveal itself. That's why it's so important to visualize frequently and not rush right into the data. And then we condition the data, or feature conditioning. Then we find the essential features. This is basically feature reduction, but we're basically removing unimportant features. And then we keep the strongest feature among collinear features. And then we engineer any additionally needed features. And then finally, if it will help, we can apply PCA to see how it might help. And because all of our features in the PCA space or eigenspace are decoupled, it makes feature engineering quite a bit easier because we can be fairly confident that in the eigenspace, we don't need any interactive engineered features. In other words, let's say in the eigenspace, we ended up with X1 and X2, and they're decoupled. Well, if they're decoupled, there's a good chance we don't need X1 times X2 or X1 squared times X2 as an engineered feature. But then again, we still have the burden of going back from the PCA or eigenspace to the original space to make things explainable. And that doesn't preclude that we can't use another model that was in the original space to explain what's going on, but it would be nice to add the explanation of the interactions between PCA space and the original space, or eigenspace in the original space. But after we've done all that hard work that we've been doing all these months now, because we only meet once a week, obviously we would have been done faster if we were meeting multiple times. Now you're ready to try different models and pick the best one for your current data assets. So just to get ready for this, let's first create some features. We're going to use our fake data skills to do that. And I'm going to go ahead and turn them into column vectors, or really column matrices. That is a matrix that's a single column. So you can call it a vector too. And then I'm going to just stack those together. I'm going to call all my features X. And I'm going to, because of other lectures, I'm going to ask y'all to trust me. This worked well. Now notice, I'm only going from 0 to 1 and I'm creating 1,000 points. What have I done? I've created features that don't need to be scaled. That's all I'm doing here. Now I create my label with the model. So we're in profit mode, of course, and those are going to be my weights. So this is going to be super simple. I'm creating a max noise. It's 4% of the max of these Y's. And then I use that as that 0.04 times this peak. So it's really 0.016 times this Y peak noise. Why do I do that? Because I want to normally distribute that data from about negative 0.05 to 0.05. So I'm just adding that randomly normally distributed noise back to my Y, so it looks more realistic. And so I'll run that one, rerun this one. And so now I have normally distributed noise like that I've added to my Y, to my labels. Okay, the next thing we want to do, now we're starting out simple. You might be thinking, why are you doing a simple train test split when you preach cross-fold validation so much? I will explain, but let's start and then I'll explain later. So, and here I explain a little bit. We don't always need to start with k-fold cross-validation. It can be a little expensive. So let's start with basic train test split. And this is a very elegant tool. You could code this yourself, but if you go look, oh, I should have kept this as a screen share, but if you go, I've created a link for these, and you can go to the documentation for this train test split tool. And I'm picking some of the parameters for this class. Obviously, we want to send in our X and a Y, and I'm just declaring the test size that I want as a fraction, as a decimal fraction. And I'm using random state, and I'm going to ask Jonathan a hard question. Where does the number 42 come from? Why do we like to use that number? Because in the Hitchhiker's Guide to, oh, go ahead. I gave it away.
No, I was going to say, yeah, I don't know. Sorry.
It's the answer the computer gave in Hitchhiker's Guide to the Galaxy when they asked it the meaning of life, or so well, you weren't specific enough. So this is our answer, 42. I think that's why I actually thought that must be why whoever wrote this example in the scikit-learn documentation was messing with us by choosing 42. So we, and then notice I use this shuffle equals true. This is nice because I get to do shuffling and the size of the test set and establish the test set, as Kimberly's been good to remind us to do. And then I go ahead and print the dimensions just to make sure, yep, it gave me the dimensions I wanted. So here are my two training shapes and my two test shapes, 200 by 1. So now you've seen me do this before. I've shared this in another lecture. This is just a function I used, just dump a whole bunch of metrics that I like. So those are there for us. We'll look at more than we need. Now we're going to go through all, and there are more models than these 8, but I like to run through these 8. And that's linear regression, decision trees, and by the way, I normally don't use a decision tree unless it's a really simple model, because I go straight to random forest because it'll generalize better. But once we get into forest or boost methods, all 3 of these are ensemble methods. They use multiple models and they balance those multiple models. And so that's why they're called ensemble methods. So random forest, Adaboost, XGBoost, I really like XGBoost, by the way, both for regression and classification. Bayesian, support vector machine, and neural network. We'll use all of these. So for each of these, oh, by the way, these are still in that Google Drive folder that I shared with. So if you go look for model selection, it's there. But we will update the course repository with all these notebooks. Okay, so we're going to start with linear regression on this test set we had. What I'm going to show you is this is a repeating pattern. I almost thought there's a famous movie in my country called The Titans, and it's with Denzel Washington and another famous actor in our country, and it's a high school football movie. And Denzel Washington is up against immense prejudice, racial prejudice in this new place he comes to be the head football coach. He's a really good coach, and he just has a very simple playbook for the players to learn, and he calls it Novocaine. It's just like, so very simple play. If we learn these plays well and execute them well, we'll do great, instead of having a lot of complicated plays that you don't learn as well. And this is that scene. I wished I could have played that scene because it's really funny how he describes it. But I'm trying to be funny with you right now and say, this is going to look very repetitive. We're just going to instantiate a class. Here's the linear regression class from the scikit-learn linear model module. We get that linear regression class. We set some parameters that we want to use. And then we're always going to call fit. And then we're going to also always call predict, the two methods. You notice that in many of the scikit-learn modules before modeling, we had fit, transform, and fit transform. Scikit-learn is really good about keeping a simple playbook. That's what I'm trying to get at. So we're gonna follow this pattern over and over with some small exceptions here. I really like to look at the coefficients when I'm using linear regression. So we'll run this. No surprise, we get a very high score. This is just a model score. I'm pretty sure it's R2, R squared. And so we've sent an X train and Y train, and this is the training accuracy. But now we want to see how well it works on the test data. And we see we get low mean squared error. We get low root mean square error. We get low mean absolute error. We get very low median absolute error. We get essentially almost 1.0 for R squared and a little bit less for adjusted R squared. Why are we not getting 1.0 though? Who can tell me that? We got pretty close to the weights that we knew prophetically we should get. Again, if we hadn't created fake data, we wouldn't know how good these are. But then we get a hint how good they are because of this. Well, it's just because we added the noise. If I took out the noise from our fake labels, these R squareds would have been 1.0 for all of these. Okay, so now, oh, and notice too, I've created, when you instantiate, I've shown the possible inputs at instantiation. Here, I did not create an intercept or a bias. So I just said, don't worry about that. And I don't want to mess up. I'm going to go through so many examples. I don't want to corrupt my X copy. So I want this class to make a copy of it. All right. So now we're going to go through the same pattern with a decision tree. And here are all the things you could call in decision tree. Uh-oh. I need to update this. And this will be nice because we can see, I thought it would autofill. There we go. Decision tree regressor. It knew that because I'd already imported it. I'm looking up here. And I'm just going to take all the defaults. We might have some fun here. I don't think there's a copy X. It must do that automatically, so it won't corrupt our copies. So I'm flying blind here because I made that mistake. Let's see how we do. Okay. Yes. So it doesn't have coefficients because it's a decision tree, but it will likely have a score because scikit-learn is really good about being consistent this way. Okay. A decision tree works quite well. In fact, it's got better training accuracy than the linear regressor. And now I can test that. Uh-oh, it didn't do as good on the test data. But look how accurate it was. It was super accurate on the training. So basically, a single decision tree does not generalize well, is what this is telling us. If I get super high training accuracy, but just kind of okay, relatively speaking, test accuracy, that model's not going to generalize well. Now, I could play with certain hyperparameters, but let's move on. I'd say, well, if I had a bunch of decision trees, I think that would do better. And we would be right. So, oh, not as accurate as a single decision tree, but, oh, look, this R squared is pretty decent on the test. So this random forest certainly generalizes better. But what could we also do? We could increase the number of estimators, and we could create a for loop to run through different in estimators. And so basically, we would put all of this in one loop and look at the effect of different numbers of estimators. What's another thing we could look at? The max depth. When it's set to none, it does some automatic mode. If you go study the documentation, what are the min sample splits? You could play with all of these hyperparameters to help improve this R squared adjusted. But right now, this is pretty good. And I just want to go through the playbook. Now we look at Adaboost. And Adaboost is known to be very good at generalizing. So there's the link to the Adaboost documentation from sklearn. Again, it's one of the ensemble methods. You can see so is random forest. It's from the ensemble module. And I'll run this. Oh, this is not as good a training accuracy. But when I run this, it's very close here. Now, what could we do? Well, the N estimators are only 50. Why don't we do that trick I was just talking about? So I purposefully decided I would wait till we got in this lecture to do this real time. And so now I've got Y predict, oh gosh, Y predict. And just for readability, I'll put this that way, and we're going to need this over a couple. And so I just want to do an exploration. This is like a grid search. It's a hyperparameter search for SDs. I like to call it these. Now I'm going to do a group. And I see that the default again was 50. So just for grins, I'm going to start with 20. Yeah, we'll go 40. Just do a few. Oh. And then when I print these, I just want to go ahead and also print in F in estimators equals SD. I call it just one SD. And then let's go ahead and make this a little easier to look at. oh, this isn't going to help. I'm going to take that away and just use some extra white space instead. So at this point, we'll just print. This is redundant, but I'm going to just give some good white space between them. And so we'll be looking at the number of estimators. And let's just see how we do here. Okay, for a 20, here's our training accuracy and our adjusted R squared. 40, 60. Oh, shoot, it's, no, wait a minute. You see the problem? I'm not really sending it in here. So I need to say, I didn't do anything. I used the default over and over. In estimators equals SD. Okay. Oh, that's really bad. Look at this. And then it gets a little better. To make the, if I really wanted to improve this, I would probably put training accuracy equals, so it would line up with those. But I'm basically each time looking at how did I improve my training and my test accuracy. And when I got up to here, it's starting to make a difference. So maybe I need to change this loop. Now, one thing I like to do, just to kind of keep a record, is do it this way. And now I'll comment out this one so I don't get a syntax error. And instead, I'll repeat my 100 so it's easy to look at. And I'll go 200, 300, 400. And not getting a lot better, but it did help to play with that. And we could go play with other hyperparameters, but for now, let's move on. Let's try XGBoost, and I'm going to start with in estimators equals 10, which is the default. And look at this. This is, oh my gosh, that is really horrible. And here, yeah, what is going on with XGBoost? Well, I wanted to do the same thing I just did above here. And what's nice, this is again like a playbook. And so I can pretty much repeat most of this stuff. But what I'm going to do is put in the XGBoost stuff. So I should have had this down one lower. I set it up so I wouldn't forget to redo this. I'm going to do this way though. Let's see, we know we're going to use that again. So let's just copy this stuff. And y'all make sure I don't forget that we have to make that in estimators a variable, of course. Now we want to look at these.
Tom, I've got a question.
Yeah.
So as we start looking at these other models where we're looking at the number of estimators, right? And we can go and you iterating through different numbers of estimators, and different models have these. How do you know when we start adding these hyperparameters, how do you actually choose the best model? Is it the one that has the least amount of estimators or the most? How do you so you've got all these hyperparameters going in, the depth, estimate, and number of estimators, and you could go through it. You could have one that has 5 and one that has 200. They come to the same generalization, but which one do you choose for your model to run? Or do you say, well, we're going to use both of them in parallel, and then as soon as there's a huge deviation in one of them, we need to revisit?
I love this question, and I hope this doesn't sound putting off, but if I'm finding that I'm seeing this kind of trend where it's approaching an asymptotic limit, I'm going to use the smallest model possible. I will always do that. Now, I might, if I saw that 300 and 400 were the same accuracy, obviously I'm going to choose 300. But if 400 was only a tiny bit better accuracy, I would still use 300. And then when I get to the cross-fold validation part, I will look for the one that generalizes the best. And typically it will be the smaller model. Now, the reason I don't do cross-fold validation at this stage is just because it can be expensive. We're using a very simple model, but some models get pretty big. And I love cross-fold validation, but I like to use simple train test splits to figure out which model algorithm is going to be best for this current data set or these current data assets. And then once I find the model that appears best, I make sure it generalizes well with crossfold. So let's run this, and I think we'll be very happy with what we find. This time I didn't waste time with, notice we started with 10. I jumped up to 100 this time and boom. Oh yeah, that's all that XGBoost needed. It just needed a higher number of estimators. And I should be printing out, I forgot to do that. Let's go, I'm gonna be lazy and go copy that from up here, print in estimators. So we'll rerun that so we can see more easily which accuracies belong to which number of estimators. So at 100, we're already doing much better. And I'll let y'all rerun this for the other, but 200, even better. Look, is that really worth it? We can test that in crossfold, but here we might decide, oh, I'm going to zoom in on 250. We could go try that, but not getting a lot of extra love for going up. But on a model this fast, we might go ahead and just use the 400. Okay. So, and again, we've only searched on one hyperparameter. Notice this other hyperparameter we have on the depth. We could look at the effects of, well, if I'm at 100, which did pretty good, what if for 100, I experimented with the depth? We might get really better returns for the depth than the number of estimators. Okay, now Bayesian. And it's actually Bayesian ridge. And I'll let y'all look at this, but notice it's part of the linear, I'll let you go research it more on your own, I should say, but it's part of the linear module set. And this Bayesian ridge class is one of them in there, but it's using a Bayesian type algorithm, and boom, it's doing great just right out of the box. And I think I could have, yeah, it gives coefficients because it's part of the linear. So do keep Bayesian in mind as one of your techniques. And ridge means it's using some form of L2 normalization too. So good tool, good generalization, and the test accuracy was great too. Now, the times I've tried Bayesian against these other things in the classification realm, it really kind of depends on the nature of your data, whether Bayesian's going to be a front runner. Now, support vector machines. There is an outstanding lecture by a professor at MIT who teaches data science. He steps through the math development for support vector machines, and he does it in a way that you guys know I would love. He uses history. But the guys that developed this are alive, and he gets to talk about it from his talks with them about, this development of support vector machines happened over time. They'd work on it a little bit and go have coffee and discuss, and then they'd come back and work on it a little more. But a lot of it is built around what we call mathematical convenience. It was like, oh, we see this, but you know what? It'd be easier if we did this, which is close enough to that. So we'll just simplify it here at this step. A lot of creative things. Very good thinking that went on in the development of support vector machines. So anyway, what's it complaining about here? It is saying I have a convergence problem. and I need to increase the number of iterations. So I did this on purpose. I'm going to try again. 2000. Still complaining. I'm going to just, I did experiment quite a while. I'm just going to go ahead and jump to what I know works. And I got rid of it. But look at this. We actually get, it's not part of the linear, but we actually get coefficients. Why is this important? It means we can use Bayesian ridge and support vector machines to get this insight into feature importance. Remember, we started with scaled features because we just made them all the same size. But we have multiple tools now, besides linear regression, that we can use to get insight into feature importance, Pareto's. Now let's see how support vector machines do on the test. Really good. Again, we're using a dirt simple fake data set with a little bit of noise, just so we understand this stuff better. Real data, not going to be this wonderful. Okay, now a neural network. Now, I was in an interview the other day, and a guy goes, Tom, tell me your experience with neural networks. And I said, well, I first learned neural networks in the mid-90s. And I coded them from scratch in C and had to use memory allocation and did all these fancy things with it. I've continued to study them and practice with them on data sets, but have I ever needed to use them on the job? No. And so I've even studied transformers and understand them and think I could code them from scratch. I've even coded neural networks from scratch in Python recently, derived, everything, but ever really needed to use it as the leading model in a data set. Very rarely. And he said, that's fair. I've had a lot of people tell me that. So it's funny. I've never really used neural networks on the job, but I still love them because I do occasionally find that they predict and generalize the best. So I think including, this isn't a deep neural network per se. In fact, the one that we're going to use is quite simple. Remember, we have 4 features. Well, how many neurons are in my one hidden layer? 2. That's how simple this neural network is. But I could have put a tuple here, and I could have said, well, and then I'm going to have another one with 2 and another one with, this would be crazy, of course, 4. These don't define the input and output layers, just the hidden layers. And but because I'm only doing 1, I only need to put it like that. But otherwise, you put them as tuples, and this is a little misleading. But if I was going to have more than 1, I'd need to put brackets around this before I form the second number. All right, but regardless of that, I'm going to run this multi-level perceptron regressor, which means it's a neural network. And boom, yep, I get pretty good actually. Why was that different from the one I ran before we came together? Because it's randomizing the weights. There's probably some seed in here, so I could always get it the same, but boy, I'm not finding it. Now, momentum, as you continue to study neural networks, adaptive learning rates, I'm like, why do we even bother? Momentum, now that's the 800-pound gorilla in neural network training. You want to train faster, better, more stable, always make sure you're using momentum, in any form of momentum. Yeah, you could play with different, the different feature weight on momentum, etc. You could go study with what all of these mean, but the main thing to make sure is that you're keeping this turned on. Now, rather than bore you, I found that 200 wasn't good enough even for this simple model. So I jacked it up to 2000 and it worked. And you saw it was lightning fast for this small data set. And then, yeah, it's got good generalization too. So, okay, we've done that. But like I promised, we really need to cross-fold validate this. Why? we want to see that the accuracies are consistent across the folds of test data. Well, are they? Well, sometimes I feel like using scikit-learn is like cheating, and I'm okay with that, frankly. So in the model selection module, we call in the cross-validate class, and look what we get to do. We get to tell it what estimator we want it to use. We send in all our X's, all our Y's. I'm not doing a train test split. I'm just saying, I want 5 folds. And I want to do scoring, and I want to use R squared. Now it's actually using more than that. I want to show you something here in a minute, but I'm just saying I want to use R squared, and yeah, I want to return the train score so I can look at things. Well, you can see this, what it's returning, these CV scores, it's a dictionary. I'm actually calling one of the keys in this dictionary. And I just want to look at the train score and the test scores. And so, wow. I mean, it's only 1,000 simple points, but it's 4 features. You know, I did on each of these folds, this was 800, 200. It's probably getting away with doing an ordinary least squares fit, which for NumPy inside SciPy is super fast. But look at that. That's, you know, I probably could throw in, except for the decision tree, or excuse me, yeah, the decision tree. If we, let's just do that for fun. Now, because of the nature of what we did above, this repetitive type playbook, yeah, that's what we thought the decision tree would do. It's not going to generalize well. Now we could say, random forest. And you see, with just a little careful planning, I get to, well, we can go fix those, right? It's not liking the way I'm doing Y. And I think I can fix that on the fly. I want to just show y'all. It's just, I'm used to this error message. It just doesn't want a 2-dimensional array. It wants a 1-dimensional array. So I'm going to reshape Y. And boom. And so the random forest does okay, but it doesn't even do as well as the linear regression. And I really like XGBoost. Oh, we want to use XG, lowercase, quite well. And then let's just, for grins, let's look at the neural network. Now that's going to take a while. Oh, what did I do wrong? Neural network was the last. Oh, I need uppercase NN. That would have followed my pattern better too. So a bit more expensive here. And oh yeah, it doesn't like the convergence problem, but it still got it for us. Yeah, I'm having convergence issues here for sure. But basically on some of these, so let's see if we can go fix that. I thought I'd already done that. Max iter. What was this again? Let's see if we can figure this out. Okay, so we have the time. Let's move this down here. And just to make it a little unique, I'm going to call it an artificial neural network. And I'm going to tentatively, this is just going to wait. I hope we're not waiting too long on this. And then I need to change this to an, of course. And let's see how we do now. Maybe we'll get lucky here, but it's going to take a while, obviously. And this would be one of the pluses for something like XGBoost, but you can see the neural network did pretty good here too. Now, what went on here? Something really crapped out. So we may think, nah, I don't want to use the neural network. So from what I remember, linear regression did quite well, but let's do the, what was the Bayesian? That would be interesting to see. And if you're thinking, Tom, why didn't you just navigate with your table of contents? I would say, because I wasn't being very smart.
No,
Yeah,
I'm
Jonathan.
thinking, Tom, why didn't you put the models in a loop?
I have done that. And I wanted you to come up with that, Jonathan, because you should do that. You can actually, yes. And I have created a system to do that before, but I want y'all to do it from here. Because if I had gone straight into that, it wouldn't have been easy to see, oh, you could just put these in a loop. And you're absolutely right. So I'm going to try the BR. And yeah, it did great. So again, we're just wanting to see, and if these weren't all super good, what I'd be tempted to do is say, okay, these are the accuracies. And then I would look at that. I would look at these for each modeling type, as Jonathan just suggested. I would put each of the models in an array, and I'd cycle through those model choices in that array. And then I would look at the average accuracies and divide those by the standard deviation of those accuracies. And I'd probably do more folds. And then once I started that run, I'd go make some tea or some coffee. And maybe when I came back, it might be done. But if it wasn't done, I'd go get a snack. I'd go check on LinkedIn notifications, etc., messages. And I'd come back and check, and sure enough, which one am I going to pick? The one that had the highest balance of accuracies in a tight distribution. But that ratio of average accuracy over standard deviation of accuracy will tell me that. But I still like to look at more than that. Always be thinking, don't trust one metric all the time. Always be challenging yourself. How can which metric is best for this problem? Is there a new metric I can create that's good for this? But Jonathan, thank you for pointing that out. And shoot, what could we do? It would be easy, even with the time we had left, but I'm not going to do it. I'll let y'all do it. I could create a list. I could call it mod list. And then I can put all those models in here. So mod, oh, thank you. Thank you, Google Colab, which is using, from as near as I can tell, some form of Visual Studio Code, because a lot of the editing works the same. So what did I have next? I might not use all the, I might decide, I'm not going to look at decision tree. I think I don't want to put random forest in the mix. I'm looking at the ones that I was really happy with. So I did like Bayesian Ridge. I did like, I'm not going to trust the neural network in this case. I love neural networks, but in this case, that it didn't complete a successful training on each fold, I don't like that. And we saw that the neural network failed, but boy, I was quite happy with that support vector machine. Let's just say that's my list. Now I go through these and I might put this much of all that in a loop. So now I'm saying for mod in mod list. And then here, I'm just changing this to mod. And then I also want to say which mod I'm using. Now this gets a little dicey. I need to create a dictionary here if I'm going to report which one, but what would happen? Print mod. I'm just curious. We'll see what it does. It may be gobbledygook. And then here, I obviously, and I'm going to do it a cheesy way this time. And I think this will go pretty fast between these. but I would want to see more. But look what it did. It just told me, oh, you're using the linear regression class. You're using the Bayesian ridge class. You're using the linear support vector regressor class. Well, that's awesome. Thank you for reminding me of that. It's even telling me what hyperparameters are chosen. Isn't that awesome? But this is still not useful yet. I'm more concerned about the test scores. And I really want to make sure, I care about the training scores too. I care about them relative to one another. But I would say I'm more concerned about the ratio of test to training for it to be as close to one as possible. That is, again, test divided by training. It's not going to be one, but I want it to be close to one. And again, like I said, then I kind of care about the average test score divided by the standard deviation of test scores. And so that I can do that, I might change that to 10. I hope this was helpful. There's so much more we can do. You can also explore all the other keys that are in this cross-validation scores. There's quite a bit. There's training times. In fact, why don't we do this? Let's just do and I'm going to do something a little strange. I'm just going to print CV scores, and we get to see more this way. Well, what's going on here? I could use a pretty print, that would help. But fit time, here's the array for fit time. Wow, that's a useful. Score time, how long did it take to run the scoring? What were the test scores? What were the train scores? I've got all that extra information. Super nice. I could create a key list and then print each key and then print the array for that key. But what I'll do is turn it back to what it was, so it'll be that way in the notebook. When y'all open it up, and then you can modify this stuff as needed. All right, questions? Guy, you had one earlier. I saw you go off mute and back onto mute.
No, it wasn't a question. First, it's very nice the session today, but I was thinking about that all what we did here, it can be first automated, second run on parallel. So I was thinking about how software engineering and some other techniques can help instead of the loop, for example. And instead of comparing, how it can be automatically compared, which is this very small. Maybe if we have extra 10 minutes, within 30 minutes, I can explain it. I will add it to the classification.
Excellent, excellent. And now, here's an exercise for the students, a suggested exercise for the students. Up here, when we found ourselves needing to do a one dimension, it's a hyperparameter search, but we could have been doing a hyperparameter grid search. Now, I will do an extra lecture, just a video on my own if y'all want this, because I'm developing it. It's a scheme by which you say, these are the hyperparameters I want to explore, but it's more of what I call a log-based star search that shrinks. What I mean by that is, for hyperparameter 1, start at the default, and on a log scale, go to the left of that, in other words, less than that, and greater than that, but on a log scale. Now, if for that hyperparameter, it's the middle value that is the best one, shrink your scale and test again until you confirm that you're at the middle point. But always, I'm only using 3 points. If you've ever done a grid search and you've waited a day or more for it, you know why I'm talking this way. This is something I've done for over 30 years in other realms too. But now let's say you're looking at the next one. Well, don't immediately shrink the scale. Oh, I found on that first one that it was the right. It was the biggest parameter that was better. Okay, keep searching at that. Now you say that becomes my left or my smallest one, and create a new log scale. As it's shifting back and forth between 3 points at a time, when it lands on the middle point, then say, okay, I'm at a middle point. That's the best one. Now I'm going to go to the second hyperparameter that I'm searching. You repeat that scheme. When you're at middle points on all of those, you shrink them all and start again until you've gotten to the smallest scale. Now you might think, oh, that sounds complicated and expensive. Not near as complicated as a multi-dimensional grid search. And because it's done on a log scale that can shrink as you zoom in, you're basically finding the best macro hyperparameters, and then you're zooming in. Now, is there a guarantee that you haven't hit a local minimum when there is a global minimum or maximum, however you want to look at it? No, but it's sure a lot less expensive than a full grid search. And it's very rare that you're going to hit a local minimum on hyperparameters, in my opinion. But it's something to keep in mind. After a lot of grid searching and this other method, by the way, just like you see scikit-learn creating all these generalized classes, like, look how elegant this crossfold was. I mean, does it get any better than that? You just send in the instance of the model estimator you're using. You send in your features and your labels. You tell it how many folds. Jonathan, I bet you could create the class I'm talking about before I can get to it. But I'm trying to do it for the book. But this is what the posts you see me doing on LinkedIn that are kind of teasers for the upcoming book, that won't go in a LinkedIn post. But if you come up with it and want to show it to me, then we can compare notes on how we approached it. But I could imagine you wanting to try this.
Which one? On this? On the...
It's what I call a star searcher.
Okay, that, yeah.
Yeah. But yeah, we can compare notes. Because of other things y'all know I'm going through, I could imagine Jonathan figuring it out for me, or Geith may figure it out for classification. But one of us will be putting it in the book, and we wouldn't mind comparing notes to your excellent code, Jonathan. You're going to be mentioned in the book anyway, so. All right, 4 minutes before mentoring, assuming everyone shows up on time. Any last questions? And we can field questions at the beginning of next week's class too. All right, I can tell y'all we're enlightened. Kim, don't talk so much next time, and I'll see y'all in mentoring.
Okay, I promise I won't.
Very good.